Welcome. In this video we continue section 2.5 and today we talk about the pigeonhole principle. Take a look at this picture. You see a box with 9 holes in it. Maybe you could call these pigeonholes. And there are a bunch of pigeons in there. In fact, how many pigeons do you see? There are 10 pigeons, and some hole actually contains more than one pigeon. This is the big idea behind the pigeonhole principle. Here we go. Claim: if 10 pigeons are placed among 9 pigeonholes, then some pigeonhole contains at least 2 pigeons. Well, this seems fairly straightforward. Let's make a proof of this. Let's assume for contradiction, because after all this is in the section on contradiction and the pigeonhole principle is something that comes about by contradiction. What is the contradiction we would use here? Assume for contradiction that what? Assume for contradiction that each pigeonhole contains at most one pigeon. That's the opposite of the claim that's being made up above. So if that's the case, then there can be at most 9 pigeons. But there are 10 pigeons. Contradiction. So that is it. That's a very short proof of the basic case of the pigeonhole principle. And this seems almost too simple to have application. But in fact, it really does have some interesting application. Generally, if n objects are to be placed into m boxes with m less than n, then some box contains at least 2 objects. Okay, seems fairly straightforward. For example, a bag contains a large number of red, white, and blue marbles. If you pick out 4 marbles, you must have at least 2 marbles of the same color. Now let me ask you this. In the example 1 situation, what are the pigeons and what are the pigeonholes? You can think about this for a second. Pause the video if you need to. So the pigeons are the marbles, there are 4 of them, and the pigeonholes are the colors. There are 3 colors. So if I choose the 4 marbles and there are 3 colors available, then some 2 marbles must have the same color. In many situations, we will see that some object can be thought of as the pigeons and some object can be thought of as the pigeonholes, or the objects and the boxes. Here's another example. Consider an equilateral triangle with unit side. So every side of this equilateral triangle has length 1. Now, if you place 3 dots randomly in an equilateral triangle, then they can all be 1 unit from each other. That is, when the dots are in the 3 corners. Now, let me just show an example. If I put 3 dots randomly, okay, there, and there, well, they aren't all 1 unit apart from each other. And if I choose 3 other dots, 1, 2, 3, a couple of the dots are really close. But what I'm really asking is, generally, how far apart can they be? And in the worst case scenario, they could all be 1 unit away from each other. Now let me modify this problem slightly. Instead of 3 dots, what if I place 4? And here's the claim. If you place 4 dots in the triangle, then there is some pair of dots with a distance of at most 1 over root 3 apart. Now, it takes a second to really understand fully, so pause the video if you need to and read this over a few times to understand what it's really saying. For example, let me just put in a few dots. So there we go. I've put 4 dots into this triangle, and the 2 that are closest, those are very close together. Surely those are within 1 over root 3 of each other. Maybe I'll try to spread the dots out more. Something like that. Is it still the case that some 2 of them are within 1 over root 3 of each other? In fact, what is the worst case scenario? How far apart could I really spread 4 dots? And so what the claim is saying is that no matter how I do it, there's some pair of dots that is within 1 over root 3 of each other. So why is that true? How can I make that claim? Here's the idea. It's kind of a cool little trick. Let's take that triangle and I'm going to split it into 3 regions. There we go. So I split this into 3 regions just like that, and now, by the pigeonhole principle, if I place 4 dots anywhere on here, then one of those regions must contain 2 dots. So now it's just a matter, actually, let me put the dot in the 4th region over there. You'll see why in a second. Now it's just a matter of figuring out in one region, let's take this region on the bottom left, what is the worst case scenario? How far apart could 2 points be? And this is where I could create the diagonal of that. And it turns out, I'll not go through all the details, but it turns out that that length is 1 over the square root of 3. And you can figure this out just using a bunch of 30, 60, 90 triangles. All right, so there we go. There's sort of a geometric application of the pigeonhole principle. Let's turn to an arithmetic application. Given any 7 integers, some pair of them will have a difference that is divisible by 6. Now think about this. Is this really a pigeonhole principle problem? Let's say that those are our 7 integers. Okay, so normally if I teach this in class, I would ask the students to come up with 7 random integers, but I will provide them there. There we go. 7 random integers. Is there some pair? Maybe there could be more than one pair. Is there at least one pair of numbers that is whose difference is divisible by 6? So the claim is that no matter which 7 integers I choose, yes, some pair is divisible by 6. Why should this be? And it's very clever. Here we go. Let's make some boxes. By the division theorem, we know that every integer in the world has one of these forms: 6k, 6k plus 1, 6k plus 2, 6k plus 3, 6k plus 4, or 6k plus 5. So these 7 integers that I've chosen, they must fall into these 6 different categories. So the 13 actually has the form 6k plus 1. The 38 has the form 6k plus 2. Can you see that? 27 is 3 more than a multiple of 6. 5 is of the form 6k plus 5, where k is just 0. 17 is also of that form. 61, 6k plus 1, and then 30 is a multiple of 6. And look at this. Since I had 7 integers placed into 6 boxes, some box must contain more than one integer. In fact, we were just kind of lucky in this case. We actually ended up with 2 boxes that had more than one integer. All we were guaranteed was at least one box, but in this case, there were 2. And what happens when I take the difference of those 2 integers? 61 minus 13 is 48, which is divisible by 6. 17 minus 5 is 12, which is divisible by 6. So it seems to hold. Now, does that seem plausible to you, that if 2 numbers have the same form, then their difference is divisible by 6? It should. And maybe here's a little bit more of a proof. Let's suppose I have a number of the form 6k plus r, where r is my remainder, and I have some other number, maybe 6l plus r, where it's that same remainder, like the 1, 6k plus 1, or the 5, 6k plus 5. When I take the difference, I'll end up with 6k minus 6l, and the r's drop away. And now I can factor out the 6, and what I end up with is a number that is divisible by 6. So that's a sketch of the proof, but hopefully it gives you the big idea that using the pigeonhole principle, I can show this interesting claim. Here's another one, example 4. Given any 7 integers, some pair of them will have a sum or difference that is divisible by 10. Well, let's take those same 7 integers that I had before. Somehow I need to make 6 boxes, and these 7 integers will fall into 6 boxes. What will it be? Pause the video if you'd like at this point and think about this. This is a little bit tricky, but I encourage you, pause it, think about it for a little while, see if you can come up with a solution, and then when you give up, or when you find the solution, go ahead and unpause. Alright, here we go. In this case, let's look at the last digit of the number, and I'll put them into one of 6 categories. Either the last digit is 0, 1 or 9, 2 or 8, 3 or 7, 4 or 6, and 5. And so I start putting the numbers into those boxes. And can you see why these are the right boxes to use? My claim is that some pair of numbers will have a sum or difference that's divisible by 10. Right, so look at this. So again, I have to have some box that contains 2 or more elements in it, and we have, in this case, one box that has 3. So the 13 and the 27, there's a 3 and 7. Oh, so if I have something that ends in a 3 and something that ends in a 7, then their sum is divisible by 10. Or the 13 and the 17, their sum is divisible by 10. But maybe the overlap occurs with 2 numbers that have the same last digit, in which case that difference is divisible by 10. So in either case, some box will have multiple entries, and for those 2 entries in the box, either their sum or their difference will be divisible by 10. Pretty clever, right? Okay. Let me just leave you with this last question. Example 5. Any subset of size 6, taken from the set 1, 2, 3, 4, 5, 6, 7, 8, 9, must have a pair of numbers whose sum is divisible by 10. Here's an example. Here is a random subset of size 6 taken from the integers 1 through 9. So 1, 3, 4, 5, 8, 9. Does this set have a pair of numbers whose sum is divisible by 10? Yeah, I think the 1 and the 9, and I think that's it. Here's another example. 3, 4, 5, 7, 8, 9. Is there a pair here whose sum is 10? Or whose sum is divisible by 10? 3 and 7. So I'll not give you the answer. I'll ask you to think about this for a little bit. Why should this claim be true? See if you can use the pigeonhole principle to come up with a good solution for it. Think about what are the boxes that these numbers must fall into. You know you have 6 elements, so maybe there's 5 boxes. All right, I'll leave you with that, and this ends our introduction to the pigeonhole principle.